All right, time for today's second lectures. All right, let me remind you that we have one more week to go for this course, and 2 weeks from now is the final exam. All right, and we have talked about the grading policy. All right, okay, so be prepared for the finals. Again, let me emphasize, I have no intention to flunk any people, but we are all engineers, okay? We have to let the numbers speak. Whatever final grade you will have depends on the numbers, okay? Depends also what kind of scores you will get from the first midterm and the final exams. And as we discussed, okay, I will adjust your grades based on certain rules. Okay, so I already told you the lower bound is at least half of the class will have A minus. Okay, at least half. Okay, at least half. Okay, and let us to be more relaxing. Okay, don't be so tense. I know that I already said it several times, but I still want to remind you that although the final semester, the final midterm is only 2 weeks from now, but right after that is Christmas. Okay, you can enjoy the holiday feeling. Okay, right after that, and then year 2026, the New Year is coming, all right? And then Chinese New Year's, 2 months winter section, okay? And during that 2 months, you don't have to go to a company and work for the money. You are a student. The time belongs to nobody but you. Do whatever you want, as long as you think that's the thing that you really want to do, okay? Now, to tell you the truth, I think we are all very lucky to be here in National Sun Yat-sen University. First of all, I consider myself to be extremely lucky to be born and to grow up in Taiwan. Okay, I didn't have that feeling when I was young. When I was young, I think United States is the heaven. Okay, at least it was a beautiful country. Now I'm not so sure. But as I grew older and older, I really discovered that it's not that I'm happy with everything's happened in Taiwan. That's not the case. That's not true. But considering what I might encounter in other parts of the world, I still consider myself very, very lucky to be born and raised in Taiwan and to be able to work here almost, at least for the most part of my life. Taiwan is actually a wonderful place to stay. It is relatively relaxing, okay? The pressure is always there, but not too much. Why? Because in our society, we have a safety net, okay? To live in a world is not, sometimes it's difficult. For example, financial burdens can be big issues for all of us. But in Taiwan, you don't have to worry about financial burdens from education because the tuitions is much, much lower than many other countries. Our tuition is really inexpensive. really inexpensive. For example, your tuition, the money you pay to our university only cover, I think, about 25% of the cost of the budget of this university. I'm telling you the truth. You can check it out, okay? It's all in the internet, okay? And so most of your tuitions, or I should say, most of your educational costs is actually covered by taxpayers, okay? So even I'm a very, very poor person, I just don't have money to pay for my tuition. You can always borrow money from the government, and the interest rate is very, very low. Don't worry about paying back. If you cannot pay back, the government won't run after you. Have you ever heard any people was being thrown into jail just because they cannot pay their students' loans? I'm pretty sure many people have not fully paid their students' loans. Okay. Of course, there will be some legal procedures, but it's not serious. Okay, there is no serious consequence. The other important financial burden is medical cost. In the United States, medical cost is the number one reason for bankruptcy. That is something we don't have to worry in Taiwan because we have a health policy, public health policy, pretty much cover every people in Taiwan, okay? At least every citizen in Taiwan, sometimes not even our citizens. So living in Taiwan, okay, is actually not that stressful. And there are so many beautiful places I can go to in Taiwan because of our landscape. Only probably take at least 2.5, at most 3 hours. You can drive from like places like urban region like Kaohsiung or Taipei City to mountains, which is 2,000 meters or even 2,050 meters above sea levels, and enjoy different landscapes. You cannot do that in United States, at least in the most region of the United States. It's just not possible, okay? So Taiwan is really a beautiful place to live, to stay, okay? So in this coming winter section, enjoy it, okay? All right, let's go back to bandwidth, okay? Bandwidth is a useful and widely used general indicator of speed response. Okay, it is even more general than time constant because time constant is defined specifically for first order system. However, bandwidth, the concept of bandwidth can be applied to systems of any order because any linear time invariant system have its own magnitude body diagram, magnitude plot. Okay, so bandwidth in that sense is a very general and therefore widely used indicator of speed response. Okay, especially during the design analysis in frequency domain. However, it should be interpreted alongside other performance and robust measures. Okay, so it's not the only factor you need to consider because as we shall see in the later part of this course, increasing bandwidth might have some side effects. All right. Now, the next topic we want to talk about is the impact of an additional ZEL for underdamped second order systems. Up to now, our focus, let me put it this way. We all know that in the X domain or in the frequency domain, transfer function can be represented like this, where P and Q are all polynomials of X or frequency. Now, the roots of this Q, which is the characteristic polynomial of the system, is called poles. And the roots of this polynomial is what we call 0. Up to now, our focus is on poles. It's not that we never talk about 0, but 0 really is not, we have not intensely discussed the impact of zeros. There is only one exception. That is non-minimum phase system, okay? In that case, we have unstable zeros. Now, we want to specifically talk about an additional zeros, stable or non-unstable, okay? Now, for a second system with an additional zero, its transfer function looks something like this. Originally, for a second order system, its transfer function looked like this. All right? Okay, so now we have an additional zero, which is located at -a. All right? So the numerator includes the factor, this factor, omega n squared divided by 2a, rather than just a zero. Why do we want to do that? Well, why do we want to have these additional terms? The reason is that we want to preserve the original system DC gain, all right? Because, let me put it this way. Originally, this is what we have, right? For the standard second order system without zero. Now, when it comes to DC gain, X should be set to 0. I'm sorry. S should be set to 0. If S is 0, this is 0. This term is 0. So what we left with is, of course, this, which give us a value of 1, okay? So due to this numerator, for a standard second order system, our DC gain is 1. What does DC gain means? DC gain means the amplification factor of the second order system, of a system to the constant input, all right? Because S is equal to 0, which means 0 omega is equal to 0. And when omega is 0, that means the system is facing an input, a constant input, because it has no component that will vary with time. Now, same thing happened here. Okay, if I have this term, then when X is equal to 0, then this becomes 0, and this term becomes 0, and this can become 0, and these two cancel out. Then what is left is this and this, okay? Apparently, the final number is 1 when S equal to 0, okay? So this term is introduced to preserve the original system DC gain, which is 1, and ensure that transfer function matches the true scaling of the closed system, all right? So where did this additional 0 come from? Can I do without it? Probably not, okay? Because here we want to examine PI control for first order system. Now, this is a first order system where tau is a constant. Here, when we set that, let's set up a feedback control system. And this is our controller, which apparently is a PI controller because this part represents the proportional control. And this part represents the integral control. And then by using, we all know that for feedback system like this, negative feedback system like this, transfer function is actually 1G over 1 over G, where G in this case is the product of these two transfer functions, which appear here, also appear here, all right? Now, let me rearrange this representation. The first thing I do is I multiply everything with, I multiply the denominator, both the denominator and both the numerator and the denominator by x times tau x plus 1. And this cancel out. And these two cancel out with the other, all right? And then x times this term, okay? So this cancel out this, give me ki. And by multiplying s with kb, give us kb times s. I can do the same thing to the denominator. When I times x with 1, okay, when I times x with, let me put it this way. When I times s with 1, okay, it will give me s, which appear here, all right? And then I times x with the remaining term will give us this result, all right? Now, and again, let me times everything with 1 over tau, all right? And this is what I will get. Why do I want to do that? Because I want to convert the leading coefficients of the denominator of this transfer function to 1, okay? So this is exactly what I get, all right? Now, this is actually the transfer function of this feedback control system, all right? Now, let me compare this with this term by term, okay? Remember, this is the transfer function that we just defined, okay? A standard second order transfer function with additional 0, all right? So let's compare the transfer function of this feedback control system with the standard second order with the transfer function of the standard second order systems plus an additional 0, all right? Term by term. This is actually this, all right? This is actually this. Similarly, this corresponds to this, and this corresponds to this, okay? I hope it is easy for you to see because for this term by term connections, I use colors to identify their relationship, all right? So if this is this, then 1 plus Kp divided by tau should be equal to 2 eta omega n, where eta is the damping ratio and omega n is natural frequency. This give me equation 1. If, let's say, this is equal to this, then this gives us equation 2. Finally, if this is equal to this, okay, I'm sorry, if this is equal to this, then Ki over Kp is actually 0. Okay, it's actually A. Now, From equation 1, what do I get? Okay, equation 1, if I rearrange equation 1, this is what I get. Okay, now same thing happens here. From equation 2, what do I see? Equation 2 tells us that omega n squared is actually proportional to Ki. Why do I care about this equation? Because I'm designing this controller. The first thing I do is I set up feedback control configuration. The second thing I do is I choose PI control. So after doing the first thing, a second thing, the third thing that I need to do is to determine the values of Ki and Kp, right? I need to determine the right values for my proportional control and integral control. Now, how do I determine Kp and Ki? Okay, since I'm dealing with a second order system, and since I already know the impacts of damping ratio and natural frequency on the performance of a standard second order system, the next thing I want to do is to identify how Kp and Ki impacts natural frequency and damping ratio. For example, here, it tells us if I increase the value of Ki, that is, I increase the strength of the integral control, then the natural frequency will become larger, which means increase integral control. In this particular case, increases the speed of response of this feedback control system. Okay, so this equation tells me about the utility of the integral control. Now, with this equation, I know that if Ki is fixed, is given, okay, then increases Kb, increase damping ratio, all right? So these results give me some clues of how to tune my integral and proportional controllers, all right? But this is, again, not an easy task because there is another thing we need to consider. That is the location of zero. Why does the location of zeros matters? Okay, because if we look at the computer simulation results of these speakers, we can easily see the impacts of zeros. This is the unit step. These curves represent unit step responses for stable for this kind of systems. Okay. Now, the reason why we have a family of curves is that we use the location of zero as a parameter. Okay. Now, for a standard second order system, that is, I assume there is no zero, then the step response looks something like this. Apparently, it has overshoot. Apparently, therefore, it is an underdamped system, which means its damping ratio is smaller than 1. Okay. Now, let me introduce zero. Okay. In the beginning, let's assume there is located relatively far away from the imaginary axis, located at s minus 10. Then, compared to this blue curve, with this zero, the overshoot become slightly larger, okay? But if I move the zero closer to the imaginary axis, let's say from minus 10 to minus 5, as you can see, the overshoot become even more, it become even larger, okay? Now, let me do that again. That is even more close, even closer, okay, to the imaginary axis. Now, I move the 0 from -5 to -3. Now the overshoot is even more pronounced, okay? So why is that the case, okay? Here, as we can see, a stable 0. What do I mean stable 0? I mean the zeros is on the left-hand side of the x-plane. Otherwise, if I will have an unstable 0, and whenever I have unstable 0, what I have is a non-miniphase system. And dealing with non-miniphase system is another story, okay? Is another story, okay? Up to now, people still don't know how to deal with non-miniphase systems effectively. Okay, now a stable 0 influences the system more strongly when it is closer to the imaginary axis. This is what we can tell from the results of these curves, all right? Now, here, one important thing is why this is happening, why this statement is true. What's the reason behind it, okay? These are the results given in the time domain, but the real reason is hidden in the frequency domain. Now, here, we saw this slide before. Here, what we have is the spectrums for a simple 0, okay? Now, these are the mathematical derivations for setting up the asymptotic statics, okay, for a simple 0. Similar to a simple 0, okay? Here, we identify the corner frequency, okay? But here, T is not time constant. Time constant come from the characteristic equation, come from the denominator of the transfer function. There is related to the numerator of the transfer function. So this is not corner frequency. But you can think of it still as a break frequency. After all, it breaks the amplitude response of the system of the simple 0 into two parts, into two regions. Now, for a simple 0, the amplitude spectrum looks up, actually say that magnitude plot of a simple 0 looks something like this. It goes in this direction. That is, the slope here is minus dB per decade. But for 0, its impact is exactly the opposite, okay? Instead of decaying with a rate of 20 dB per decade, it actually increases with the frequency with a rate of positive dB per decade, all right? So what happened is that this tend to increase the bandwidth of the system, right? Because by definition, bandwidth is where your frequency drop minus 3 dB. If I introduce a 0, it will reverse this decaying trend. So I will probably reach the minus 3D standard or the 3D level in much higher frequency, okay? So here, remember that what we have is this system, okay? Let me break it into two parts. The green part represents zeros. and the blue part represent the standard second order system, okay? Let's just ignore A for the time being, all right? Okay, now, remember the reason why we want to have body diagram. We want to use the magnitude plot of the body diagram in the first place is when it comes to the amplitude spectrums, we can add their frequency response curves together. Here we have multiplication, but when I take log, this multiplication convert to addition, right? Remember that. Now, for the Z, okay, it's amplitude. There are two ways. These two parts can be put together. Okay, the one is this, the other is this. It all depends on which subsystems stop to break away. Okay, which subsystem stop its so-called breakaway action earlier. Okay, now for this case, because the Z contributes a positive 20 dB per decade slope only after the break frequency of omega 8, right? Okay, the break frequency for the Z is here. Okay, increasing A push this effect into higher frequency. That is, if you increase A, this effect of this positive 20 dB effect will move to high frequency. For example, from this to this, all right? Making the Z irrelevant in the low frequency region. Why making it irrelevant? Because if this is the case, if the natural frequency of this second order system, which is located at which is approximately the break frequency of the second order system, if it is located here, then this minus 40 dB per decade impacts appear earlier than this impact. So since the slope of this curve is minus 40 dB per decade, so in comparison, this positive 2 dB per decade increases become relatively insignificant. It will be large, almost it will be cancelled out by this factor, okay? So, but it can be the other way around, okay? Decreasing A shift the effect into lower frequency. As a result, Z significantly amplifies the resonance and produce overshoot, okay? Because it appears earlier in the frequency domains. And therefore, it will most likely increase the bandwidth. And then system will move faster. But the cost, the expenses, the price we need to pay is that resonance can be amplified, and we might have larger overshoot. So what we are seeing here is that the location, I should say the relative location of the pulse and theirs really matters. This is an ideal case. By contrast, this is a non-ideal situation, all right? Now, let's look at the impact, all right, okay, of the relative location of Z and damping ratio, all right? Here, what I have here is, we all know that this is the magnetic plots of standard second order system, which is turned on when the frequency increases to the natural frequency of the second order system. Okay, the impact of zero on the transfer response depends on whether it's 20 dB slope at omega A turns on. Okay, before or after the pole of minus 40 dB per decade slope, when A is smaller than omega N, turn on before or after this minus 40 dB slope action, okay? When A is smaller than omega N, the zero strongly amplify the resonant peaks. But when A is much larger, its effect is become negligible, all right? Now, let's demonstrate that by showing the unit step responses with different zero to pole distance ratio, okay? Now, A is the distance between zeros and the imaginary axis. And eta omega, and remember, the root of this characteristic equation is minus omega n plus j omega d. Remember that? Where omega d is the damped natural frequency, which is omega n times the square root of 1 minus eta squared, when eta is smaller than 1. Okay, so here we are talking about underdamped system. So here, the parameters is the ratio between the distance of zero to the imaginary axis to the distance of the pole to the imaginary axis. Okay, now this ratio determines which frequency will appear earlier in the frequency domain. All right. Now, when this ratio is very, very large, which means A is much larger than eta omega n, which means this will happen. And this frequency is about 10 times higher than this frequency. All right. So the high frequency components enhancement impact caused by the zeros, in this case, become negligible. All right. And therefore, its unit step response is very similar to that of a standard second order system. However, if I move the zero closer to the imaginary axis, therefore the ratio drops from 10 to 2. As you can see, the overshoot increase dramatically. If I go one step further, that is, the pole and zeros, the distance to the imaginary axis is actually the same, then the overshoot become even larger. And it will become very large when this ratio has a number of 0.5. Okay, so that is why zero matters. And how much impact a zero has really depends on this ratio. That is zero to pole distance ratio. Okay, when I mean distance to the imaginary axis. Okay, now, so the figure on the previous slide shows how acting a zero to a second order system changes the step response. The first thing that you need to know is here, for the horizontal axis, the variable is not t, but omega t, all right? We talked about that before. This is a normalized time. So the horizontal axis is normalized time omega nt. So higher frequencies produce faster real response, because if omega nt, let's say it's a fixed number, let's say just 1, all right? Therefore, t is equal to 1 over omega n. Therefore, if omega n is larger, t is smaller, which means to reach, for example, the peak for this system, okay? When omega n is larger, the real time, the number, the real time is actually much smaller, okay, when compared to when omega n is small. All right, here the ratio A over eta omega n quantify how the zero's distance to the imaginary axis compared with that of the poles. Okay, so this is the concept of the relative distance. The element 0 or pole that lie closer to the imaginary axis dominate the transient response. Which one matters really determines which one is closer to the imaginary axis. And that means which one is turned on earlier in the frequency domain. That is, this explanation actually justify the devotion of our study to frequency domains. Because without the concept of frequency domain, it is very difficult to explain why a stable zeros can have an impact on the systems, and why its relative location with respect to the pole really is a dominant factor when it comes to the transient response of such a second order systems. All right. So to prevent overshoot and have response that is closer to the standard second order system, you need the zero to be located further away from the imaginary axis compared to the poles. Therefore, let's go back to the PI controller. Why designing PI controllers is difficult? Because here you only have two parameters, Kp and Ki, but you have three set of conditions you need to take into account. First, when it comes to speed, you need to consider omega n, all right, which is natural frequency. When it comes to the relative stability, you need to consider damping ratio. Now, because there is an additional zero, where A is equal to Ki to Kp. And what you need is you want this A to be large, at least large enough, because you want to push A further away from the imaginary axis, further to the left of on the x plane, okay, to prevent this zero to dominate the transient response, which will generate redundant overshoot. And that is something we don't want. So there are trade-offs that we need to make to balance these three considerations, to balance these three specifications with only two parameters. Okay, to examine how it impacts the overshoot, this figure is really helpful. Here, on the horizontal axis, what we have is percent of overshoot. Here, on a vertical axis, what we have is A over eta omega. And again, okay, this represents the distance of zero to the imaginary axis. And this represents the distance of the pole to the horizontal axis. So this is really the ratio that matters for this so-called a second order system with additional zeros. Now, what can we learn from this curve? Okay, in this era of AI, I strongly urge you to use large language model to help you to learn. For example, you can copy this image and upload it to a large language model, such as ChatGPT or Gemini, okay, or Claude, of whatever you prefer, okay? Some of them are even free of charge. That means you don't have to pay anything. I strongly advise you to get a free student's account of Gemini. The Gemini is made by Google, okay? It wasn't such a good large language model until very recently. They released their newest version, and their newest version has received comprehensive, extensive positive feedbacks. Many people talk about Gemini 3 and get and recommend Gemini 3. And the good thing is, as a student, you actually can get a free account. That is, an account without paying anything, okay? It lasts only for 1 year, okay? But at least for the next 1 year, you can use it for free, okay? Not as much as you want, but you know, there is always limitations. But I think a 1 year free account can already help you to do many, many things. For example, you can upload this image and you tell the large language model, okay, what is this image? Where does this image come from? It comes from this transfer function, okay? And the next thing you can do is ask the large language models, what can I learn from this figure? What information are embedded in these figures? What does this figure really tell me? Okay, and you can even ask the large language model to respond in a point by point manner and use a learning friendly tone. Okay, so since it's learning learning friendly, so you can expect its response to be relatively easy to understand. All right, I strongly recommend you do that, not just for this class, but for your future study. So what can I learn from this figure? The first thing I noticed that, okay, this is the overshoot, and this is the ratio of Paul, observe respect to Paul. And the second thing I noticed that is there is a family of curves, and the parameters for such a family of curves is 8. All right, so it means different damping ratio give me different overshoot. All right, so one damping ratio, one curve, one damping ratio, one curve. Okay, apparently damping ratio has something to do with overshoot. That is not surprising because let me go back to where here. Okay, we saw this figure in the previous lecture. Okay, for a standard second order system without any zeros, the overshoot depends only on damping ratio and damping ratio only. Okay, it has nothing to do with natural frequency. All right, but here things are slightly different. Okay, in this figure we can see that for a standard second order system, as damping ratio become smaller, the resonant peak becomes more pronounced, more distinct. All right, so this is exactly what we have here. because as the value of eta decreases, this family of curves actually move in the rightward direction, which means it becomes larger when it comes to percent overshoot. All right, 11 o'clock. Let's take a 10 minutes break. 谢谢。